we go to a new topic, differential amplifier, which is very important. We learn all the basics. We learn common source amplifier, common source with degeneration, source follower, and what else? Common gate. And then we learn cascade to enhance the gain. And then we also learn current mirror. We make current source. We also learn current source, a simple one, right? So now we have all this basic building block. And some of you might even say, I learned almost all of them in E122, right? But I just want to emphasize one more time. At that time, you just keep doing KCL, KVL. But now you have the insights, right? You look at the circuit, you know how to solve it if that circuit is composed of these basic elements, right? So that is the same when we go to the differential. So what is the meaning of a differential signal? Let's talk about this, right? So on the top is a single-ended signal, right? I would say all the voltage must reference to a common ground, right? I say now I'm at 10 meter. 10 meter from where? 10 meter from second floor, first floor, or from the sea level, right? I might even be negative 100 meter compared to the mountain next to us, for example, right? So reference is very important. So when I put a signal, for example, here I have a peak-to-peak signal, for example, plus minus, let's say 10 millivolts. Into here. What does it mean? It means it's reference to the ground plus minus 10 millivolt. The AC ground, however, right? We're talking about the AC signal, right? So if you remember common gate, right? We usually would say we bias it at 2 volts, for example, and then you go from 0.21 volt to 1.99 volt, right? And that is the plus minus 10 millivolt. Right? So now we just look at the small signal. And then the output after this amplifier, it might become plus minus 100 millivolt. By the definition, what is the gain? Why? Because it is V out divided by V in, right? This is the definition. And then you say, well, this one swing by 100, this is swing by 10, so the gain is 10. This is what you know already from single-ended amplifier, common source, common gate. That's what we did, right? We get the output voltage of the drain, maybe plus minus 10 millivolt, 100 millivolt, and the input to the gate is plus minus 10 millivolt, so the gain is 10. Okay. Due to some reason we will discuss later, in order to cancel the noise, it's also possible that I don't treat this as the signal. I don't reference it to ground. I try to reference it to another signal, right? It's just like I try to check if my GPA is higher this semester. Instead of just look at the absolute value, I go from 3.7 to 3.8. I try to reference to the average to the class. Maybe the class increased by 0.2. Then actually my GPA is not higher for the purpose I want to discuss, right? So here I have two signals, okay? So one of them they go up in opposite direction. For example, one will go from, again, it's plus minus, but they go at a different time. For example, at this time, this one go up by 10 millivolt. At this time, but what happened to this one? It goes down by 10 millivolt, okay? And maybe later, this one go down by 10 millivolt. This one go up by 10 millivolt. Still both of them, each of them has a swing of plus minus 10 millivolt, but they always go in the opposite direction. Is that okay? So what is the input voltage in this sense? I define it. I'm the human. I'm the one design the circuit. I'm the one use the signal. I use the signal. I interpret the signal. I define it as V in equals to the difference of them. So it's V plus minus V minus, which is 10 millivolts because they're always opposite. The swing is 20 millivolts. Do you agree? Right? Both of them swing by 10 millivolts, but they always go into opposite direction. So the total signal swing by 20 millivolts, right? Because the maximum difference is sometimes I'm 20 millivolts above of you, sometimes I'm 20 millivolts below of you. Is this clear? Why do I want to do that? Just because I want to do that. I define in this way. It's my definition. The physics is the same regardless of my definition. But now I want to define the signal in this way. But does that make sense? Yes, because later I'm use this signal to do some physical operation, right? So I only care about the difference, not about the absolute value. Okay? So this amplifier is going to amplify my signal like the one above by 10 times. So this one is going to go up by 100 millivolts. And when it goes up by 100 millivolts, the bottom one is going to go down by 100 millivolts because they are out of phase. Because when my input was going down, the output will go up by 100, right? But at this time, this is going up, so this one will go down by 100 millivolts. And again, because of the way I want to use it, I'm going to define the V output as V output plus minus V output minus. So it is going to be 100 millivolt minus negative 100 millivolt, which is 200 millivolt. Okay, what is the gain of this system? Again, by definition, it is V out divided by V in. And V out, I know it is 200 millivolts. V in is 20 millivolts. So the gain is 10. Oh, sorry. The gain is 10. Okay. So what did we do now? Looks like we are wasting our resources. I have a single amplifier. It's amplified by 10. Now I try to, because the preference of the human, I force you to have the differential signal. They always go into the opposite direction. You go up, then I will go down. And I only care about the relative difference, not the absolute value. I double the hardware. I basically need 2 amplifiers to get the differential output. And the gain is still 10. And that is the situation. Is that okay? Is that clear? Okay, so have this in your mindset. What is the meaning of differential signal? Why do we want to do that? The main reason is because we want to reduce the noise. For example, in this circuit, this one is the AC power coming from the wall, 100 volt at 60 hertz. And we have the transformer, then we have the rectifier, full bridge, diode connector rectifier. If you remember, you might want to have a very large capacitor to smooth out the circuit, the ripple, right? But if you forgot, doesn't matter. The final result is that the VDD is not going to be flat, absolutely flat. You will get some noise, right? This noise is going to cause some problem. This VDD may be, let's say, on average is 5 volts, but then you are going to have a ripple voltage, VR, plus minus VR, for example, right? Okay? So what happened to it here? Now, this one is used to bias this circuit. What type of circuit is this? Common source, thank you, CS. Because this is NMOS, so this is gate, this is source, this is drain. Input is gate, output is drain, right? and we just have the VDD biasing the V out and go to the output. So it's a common source amplifier. Yeah, what is this for? I have a speaker here, a microphone, not speaker, microphone. And it goes into here. And remember, we do need to bias the gates. Here we did not show it, right? We can put 2 resistors so that it is maybe a 3 volt. And then you just couple your voice, the electrical signal generated by your voice through this microphone to here. And then you amplify. And then you may put this to a speaker maybe, right? Eventually, I don't know how to draw this. Simple. Eventually, you go to a speaker, right? Right. This is a very practical system, right? Now, if you don't talk, you just leave it there. So if I say nothing, then what should I expect? I don't expect any small signal coming out, right? And actually, just to be, not to confuse you in the future, because you need to do this in your lab later, we actually need to add a big capacitor to do the coupling, okay? To avoid the DC signal going in, right? So I should not hear anything. But unfortunately, probably you guys never have this experience. If you're 30 years old, older like me, then when we used to have this problem when the teacher taught, it was just they don't talk, it was some humming noise because the system is not good enough to filter, okay? So first of all, you already answered the question. This is a common source, right? And then now we want to say what is the V out when no one speaking, right? When no one's speaking, then this system is like this. I have VDD plus VR, for example, from the top. And then here I have RD. And then here actually is grounded because no one is speaking. The gates, no signal coming in. This is AC ground, remember. And this is V out, right? Now, if no one talk, I expect 0 input should give me 0 output. Okay? But unfortunately, that is not the case. Because this one is just equal to VR at AC. Now, VDD is DC bias, so it doesn't change at AC. But now because of this ripple, it's just like I have a signal on the VDD. So the VDD is no longer 5 volts. It can go from 5.01 to 4.99, for example, right? So this one is keep changing. So actually, I do have a voltage source, which is AC going from VR, going from top, right? So the bottom one, while the input is 0, right? It's just like that. This one has no effect, right? What will be the output VR if I have VR? What will be the output VO when I have VR here? Huh? VDD is grounded, right? VR is just saying what is the voltage here. If I have VR here, you have a voltage source VR here, and you put a resistor in front of it, you measure the other end of the resistor, what will be the voltage on the other end? There's no current, but not VDD. Why is that? Because we're talking about AC. Just VR. Yeah. So it's just like the net effect is that I have a, maybe the best is redraw it, right? This is equivalent to I have a VR RD and then V out. That is the net effect of this one, right? Because I don't have anything coming from this transistor, right? Maybe I should not cross it, but what I'm trying to say is there's no signal coming from this transistor. Let me don't cross it because someone may feel that this is off, but it is not off. Actually, it is still in saturation, just no signal coming in, right? But I don't have AC signal coming in, so it's not going to affect the output. So this point is affected by the VDD. If the VDD were grounded, then this is ground, then Vout is 0 in AC. But now the VDD is not. VDD actually effectively has a small signal due to this ripple. The ripple is VR. So actually my output is VR, right? Is this okay? And that's why you will hear some noise. And that noise has a frequency of what? Actually, I forgot. Maybe 120 because the ripple is got rectified, right? So actually, this might be 120 hertz. Maybe I'm wrong. I forgot. Right? Go back to check. Right. So the wall is 60. Right. The ripple may be 130 hertz. But anyway, you just hear this 130 hertz. You can hear, right? Because your ear can take from 20 hertz to 20 kilohertz, right? Then you hear this so-called humming noise. So there is a problem, right? This is just your ear. Maybe you don't care. I don't care about this noise. Everything works well. But now when you go to high precision system that you really need to use to do some control, then this noise is going to hurt you. How can you cancel this noise? And that is the reason we use differential amplifier. And we'll show you why. But do you understand any question here? Yeah, here tells you the very important concept of all this small signal, right? If you really understand what is the meaning of small signal, then you should not have problem to see why I grant this and I have this. If no, let me know now or just come to office or send me an email. Yeah, question? Yeah, so here I'm trying to say that the middle is VR is at 5 volt and then the peak to peak is VR, so that plus minus VR over 2. But now the total signal is actually here the VR is the magnitude. Yeah, amplitude versus P2P. So I'm lousy in this. Yes, you can put VR over 2, depends on your purpose. Yes. How about this? Let me erase this. You are right, actually, right? To more strict, maybe we just put VR divided by 2. But as you said, here I'm referring to P2P. So now, yeah. So you are right. I just try to avoid extra trouble. Good point. Yeah. But when you come to noise, you really don't care whether it's divided by 2 or not. Yeah. Okay, so what can we do? So the first solution that we can propose is that let's do not reference to the signal to the ground. Can we reference it differentially? Now, let's think about this. I'm going to define the Vout as Vx minus Vy. So I forgot to tell you, now instead of having one single differential amplifier, I have two. A single common source amplifier, I have two. Both of them are the same, right? Although they are facing different direction. Because this is source, this is drain, this is drain, this is source, this is gate. They are decoupled, right? They share the same VDD, but they don't talk to each other. No problem, right? Now, if I define the Vout, now you do have this humming noise, but now I want to only take the difference to drive my circuit, and that makes sense, right? For example, I can connect this to the plus terminal of the speaker, this to the minus terminal of the speaker. For example, right? This is the speaker we drawn earlier, right? Instead of have one terminal connected to the ground and then the other terminal just come from the output. Now I actually try to drive them in this way. differentially, okay? So that's why V out equal to Vx minus Vy. Now, if there's no input, assume there's no input, it means V in equal to 0. So no one is talking, right? Okay. So what will be the output? First of all, what is Vx? We just say earlier, no one talking, right? So they don't have effect. We are. From the last slide, we already say that no one is talking for a single differential amplifier. The output is VR. Okay. Yes. What is Vy? Also V out. They're just exactly the same, right? So what is V out? Vx minus Vy, which is 0, right? So we don't have the humming noise anymore. So I'm done. I solved this problem because I try to have the differentiation. So here, I hope you can see the reason of have a differential signal, because all the signal share the common noise. So now it's just like that. I'm traveling on a bus, right? You will, if you look from outside, you will see that I don't travel horizontally because the bus is bumpy. So if you look from the street, you see that I'm traveling in this way. But if I force you to come to the bus with me, and maybe, how to say, or you travel in a differential bus, when my bus going up, you will always go down, for example, then you will find that you will not detect this bumpy thing, right? Because we all feel the same bump at the same time. You will only see the difference between you and me, right? And that is how we cancel the noise. As long as both of these signals feel the same noise, and because we're doing differential means subtraction, this type of common mode, what we call it common mode, will be canceled. Okay? But in this particular case, is this still useful? Is there any gain? You see that I put the signal to both sides, right? So when therefore the signal, from the signal perspective, Vx is still equal to negative Gm Rd times V in, because it's a common source. Vy is negative Gm Rd, also V in, because the same V in goes to the two inputs, right? As a result, V out divided by V in equals to Vx minus Vy divided by V in. And you see that that is 0 divided by V in. So there's no gain, right? So this is useless. Can you think of a method to solve this problem? Okay, replace M2 with a constant bias, right? Yeah. So that is a very good idea, right? But that won't work. It works in this case. There's two problems. One is that we need extra, but it's the same actually. You're right. So I make it constant bias, right? When I have constant bias, then this light is like registering the noise here, so I can always cancel it. But the problem is that it cannot solve other common mode noise that we will discuss later. It's okay to solve this one, actually. Actually, this is okay. Yeah. Do you have another way to do that by looking at why this got canceled? Okay, so one of them make it positive and one make it negative, right? That's a very good idea. The problem is that for differential amplifier, we want to make them exactly the same as much as possible. But you're almost there. You saw that is the sign, the problem of the sign, right? Maybe you're limited by drawing here. You thought that you cannot do other things. You are allowed to, so actually you have the answer already, I tell you. Just put a differential input instead of instead of common input, right? And that is exactly your solution, right? Good. So our goal is to do differential input, and that will solve the problem, right? So again, we need to define the input and output. Again, it's the human definition. Here I say V out is Vx minus Vy. V in minus V in 1 minus V in 2 is V in. You can define as Vy minus Vx. It doesn't matter because you are the user of it. You define what to do. Okay? And of course, in exam, I will define for you. If I don't define for you, either answer will be correct. Okay? Now, and that I need to make sure that emphasize again, we always make the two branches exactly the same, right? That's why we cannot do common source plus plus common gate, right? So we're going to make them the same. So let's look at the output, right? What is Vx this time? I'm asking small signal. Yeah, not the biasing. What is the output? What is Vx for the given input? Negative Gm Rd times V. Maybe I call it V in 1 first. And then you say, yes, this is just V in plus V in, right? Okay. Is that okay? This is just a common source amplifier. Do not worry about the other parts, right? You can break them into two parts. How about Vy? Gm Rd V in 2. Okay, negative Gm Rd, I put negative, I do one more step, negative V in, which is Gm Rd V in, right? Okay, now you tell me what is V out divided by V input. Remember, we don't just talk V in now, we need to follow. We say this is the input, this is the output, right? Because I care about that signal. What is V out? Vx minus Vy. And V in is what? V in 1 minus V in 2. This is given, right? Or you define it. Vx minus Vy is negative Gm Rd V in minus Gm Rd V in based on our calculation here. Agree? How about V in 1 minus V in 2? V in minus negative V in. Right? Be very careful by definition. So this is equal to negative 2Gm Rd V in divided by 2 V in. Right? That is exactly what we have been talking about here. Input is double. Output is also double. And because of this, I still have a gain of negative Gm Rd, which is the same as the common source, right? But now you can tell me why we want to do this, right? I can just use common source, but I'll use double hardware, double power consumption, more sophisticated scheme because I want to reduce the noise. Okay, so this will help me to reduce the noise. I'll eliminate the noise, the common mode noise. Okay. So here what I want to do is to just combine everything together one more time. Because just now we assume there's no noise, but I just want to assure you that this works. First of all, now we have noise at the VDD. We also have differential input here. Is it true that this is really solved? Now, the problem is that we need to draw the small signal model, because when we do the common source, we actually assume VDD is grounded, right? When we do the small signal, the GMRD. So is this still correct now? I can use GMRD. So yes, because it is small signal and the circuit is linearized in small signal, we can treat each signal independently, right? For a linearized circuit, you can have two excitation, right? It's just like, how to say, right? You push me from the left and someone push me from the front. If this is a linearized system, it's the same as I first study how I react when you push me from the left, and then also study how I react when you push me from the front, and then I can just add them together. I don't need to solve the complicated system that you push me from the left and from the front at the same time, right? But for a real system or a big large signal, right, or like human, this is not the case, right? If someone pushing me from the left, I may just move to the right, right? Someone pushing me from the front, I will just move to the back, right? And then if you say linear, then I will go in the diagonal direction, right? But if someone pushing me from the left, someone pushing me from the front at the same time, maybe I'm so scared, I just knee down, right? So this is a completely non-linear system, right? But because this is a small signal and this is a linearized system, so in this class, you can always treat the what we call excitation separately and then add them together, right? So the goal is this. Because we can do this, so we can treat them separately, right? First, treat V in equal to 0, right? And then consider VR. Okay, so what is the output? V out in this case. We did that already, which is here. When there's no input, although this is not differential, but it's the same when there's no input, right? So when this is 0, we already say that the V out is equal to 0. And this is on slide 8, right? Okay. And then we consider another excitation. When V out equal to 0, when there's no noise, then we say the V out equals to negative GM RD times V in. That is what we derive from slide 9, right? And then use superposition, because it's a linear system, then the V out equals to 1 plus 2, which is equal to 0 minus GM RD times V in. So it is negative GM RD times V in. I just try to summarize this, right? So that you won't feel confused, right? So this is a very important skill when you treat the linear system, okay? Any questions? So up to here, I show you that I have developed a system that can avoid this common mode noise. But this is just differential input, right? We have not talked about the real differential amplifier yet. We will talk about that later. Okay, so now we are at this stage, then let's study more property of the differential signal. So what is a differential signal? It doesn't need to be sinusoidal. As long as it goes in opposite direction by the same amount, and they have the same FHDC value, which we call the common mode, and they see the same input impedance, then they are differential signal. Right? For example, if I look at the time as the x-axis, and then voltage on the y-axis, I could have a signal like this. Let me also find a common mode point. They have the same common mode. And then I could have a signal like this. Okay. And if I have another signal like this, so that they always go into the opposite direction about a common mode. This is VCM. Okay, by the same amount, then they are differential. Okay, just think about the lever, right? They always just go into the opposite direction. Is this okay? Now, why this is important? Because later we are going to use some skill to analyze the differential circuit, which can simplify the calculation a lot. But you need to make sure your signal is differential. In this class, it's easy. We only talk about sinusoidal differential. Okay, so but still just bear this in mind. Yeah, square if you make it differential. This is more general than square wave, right? Yeah. Beautiful. Yeah, but square differential, yeah, you can do that. No, digital differential is the same. So for high-speed transmission, again, they go in the opposite direction. For noisy environment, and also, yeah, I think it's mostly for noise. Yeah, because if you have noise, then digital is about the number of bits you can transmit per second, the bit rate, right? So you have a lot of noise, you need to go at a lower frequency, because in principle, if you have a bit go long enough, when you do the averaging, the noise will be gone. Then you can resolve that is bit 0 or 1. Now, if you have differential, get rid of the noise, then I can have a shorter bit width, right? So, yeah. Okay.
This is it's just one signal, right?
No, two signal. Yes, yeah, it just fit, but you need to physically generate two signal, like here.
If you're saying like a microphone, it's just one signal, then you pause it and use like a buffer or something and flip it, and then it's two.
For that one, you can make a central tap to the transformer, right? And then the central becomes the ground.
Okay.
For the microphone, right? You're talking about, for example, right? What if just one possible implement, I put this as ground, right? Then these two signal will be differential about this ground. Yeah. But you do have two signal going in opposite direction. Yeah. Okay, so let's just understand more by looking at example. Like here, right, we have this sinusoidal wave. What is the common mode of this circuit? Right? Do you know how to draw this? Right, basically you will have a line here, which is VCM, right, for both of them. And one of them is sine wave. How do you draw sine wave? Right? Because at 0, this is 0, and you plus VCM. So the whole thing shifts up, right? So this is V1. Okay? And then you have another sine wave. Okay? And this is V2. Are they differential? They are, right? They have the same common mode. They're going in the opposite direction at any time, because sine omega t. And they have the same amplitude, V0, right? So what is the common mode level in this case? Right, one possibility, let me also give some numbers. For example, this can be 2 volts. Let's say this is 10 millivolts. Okay? So it means this is V0 equal to 10 millivolts, VCM equal to 2 volts. What is the common mode of this circuit? 2 volts. Yeah, very straightforward, 2 volts. VCM equal to 2 volts. Now I care about differential circuit. What is the differential signal peak amplitude? By this one itself, what is the peak amplitude of the signal? 10 millivolt. Yeah. But we are doing differential, right? We can take a look. The so-called, the peak is going to be maximum of V1 minus V2. No. Yeah, that is the peak. Okay. Yeah, that is the peak, right? The maximum. Because I define the signal as V1 minus V2, which is equals to, do you see that I have 2V0 sine omega t now? I need to put the maximum. You see that because I do this subtraction, VCM is cancelled. I really don't care what VCM you have because I'm doing differential. Even your VCM is not constant, it's fluctuating due to noise. It's not affecting my signal. I only see 2V0 times sine omega t. And what is the peak magnitude? 20 millivolt. Okay. How about the peak to peak of this signal? 40. Peak to peak is just double, right? It is just 2 times 20 millivolt equal to 40. So you do see that everything got double compared to the original signal. Okay? But the beauty is that you cancel the VCM. That is very important. Okay? Am I done already? No. Okay, I still have one more. So we done with the differential